Good morning. Today we'll discuss a topic called numerical methods which are used in CFD. This topic is in subject called computational fluid dynamics for 6th semester mechanical engineering students. Myself, I am P. Venkata Mahesh, assistant professor in mechanical engineering department in Institute of Aeronautical Engineering. Now, why we have to use these numerical methods? As we have seen, the the governing equations that we have derived, they are all partial differential equations. Now, if these governing equations are given, say suppose the Navier-Stokes equation is given, we will not be able to relate what it is actually unless we are very proficient about the Navier-Stokes equation. What is its behavior, how it look like, and I mean how the behavior of the fluid which follows the Navier-Stokes equation. All those things. If we are very proficient about it, if we have we are knowledgeable about that Navier-Stokes equation, then if someone says that the fluid follows the Navier-Stokes equation, then we can, the person can understand. Person with full knowledge can understand. But if the person is not having a great knowledge about the Navier-Stokes equation, and if he says the fluid flow follows the Navier-Stokes equation, so the problem is like that. Now, say suppose if I give a diagram like this, okay, if I give a diagram like this where the all these lines are representing the magnitudes of velocities and they are following like this, or if I give numbers, the values of the stresses at the values of velocity is varying from 0 to 0 with a maximum value of 5 meters per second at the center. Like that, if I give some values, then it is easily understandable for anyone who sees that object. Okay, so that is the reason the numerical methods are used for solving the differential equations. Okay, differential equations by themselves, they give the physical meaning behind that, but these, unless we are very knowledgeable about the differential equations, we cannot know what is the what is happening to the physics of the flow. So the mathematics, the power of maths can easily be realized by numbers or some pictures like this. So for this reason, what we do is we use some numerical methods for these governing equations, and we convert this governing equation, we'll obtain some numerical values for different grid points inside the fluid domain. So that is the reason why we use numerical methods for solving the differential equations. Now, for solving the partial differential equations, we have two methods. One is deterministic method. So what is this deterministic method is about? One example is given here. A ball is released from certain height above the horizontal ground. Upon collision, will bounce back to the height. Okay, a ball is taken. It is released from some particular certain height, and it is after bouncing back from the floor, it is reaching the same position. Okay, so if I may do the experiment or any other person may do the experiment in the same place, I will get the same answer. Okay, so this kind of experiments or this kind of method is a deterministic method. What it is, the output is always same. Okay, for the given input to an equation, the output is always same. Say suppose if it is changing, what type of method we have to use? Okay, now here if you see in this deterministic method, the output does not depend on how many times the equation is solved, or how many times the ball is released from the particular height. Okay, how many times I will release, it will give the same, it will reach the same height. Okay, so that is it is independent of the number of times the experiment is repeated and what time of day it is solved. I can release this ball in the morning or afternoon or evening or night, whatever time, or January, February, March, any time I may release, the height which bounce back will be same. And what is the computer on which it is solved? Whether the here it is said computer, so I can say the person. I may drop it, you may drop it, another person may drop it from the same height. If he is releasing from the same height, in the same place, then there is no chance of changing the height. I am releasing the same ball from the same height, but the person is different. And here the problem is same, but it is solved on different computers. Then it is going to, any computer is going to give the same answer. So that is a deterministic method. Okay, because of precision, okay, some computers may give, say suppose after a point, some 10 decimals. Some other computers may give after a point some 15 decimals. So the precision errors may be there, but the final value, if I truncate it to a particular value, then it is going to be the same. So that is about the deterministic method. The other one is stochastic method. What is the stochastic method? It is based on the statistical principles. Okay, it is based on the statistical principles. The output can slightly different from this for the same input. The output can be slightly different from the same input. It depends on how many times the calculation is performed, and other factors also. So what I will see with an example here. Say suppose I have n balls with me. Okay, and I'm releasing all the balls, n balls, from the same height. Okay, n by 2 balls would bounce to the slightly height above half the released height. Okay, half of the balls are bouncing to a particular height above the midpoint of the height from which I am releasing. Okay, and remaining n by 2 balls would bounce slightly below the released height. Okay, so half of the balls are rising to some height, half of the balls are rising to the another height, such that in the end the mean height would be equal to the half of the height of the release. So half of the balls are rising below the midpoint, and half of the balls are rising above the midpoint of the height from which I am releasing these balls. So this is not a precise solution. It involves some statistics. How this many balls are thrown, this many balls are thrown, like that. So if I change the number, okay, if I change the number, if I take 100 balls, I will get one result. If I take 200 balls, I will get another result. So like that, it depends on number of balls which are released. So it may change the value. Sometimes it may come same value. Sometimes it may come a different value. So this kind of method is called a stochastic method. Now in CFD, what methods are used? See here, the FDM, FEM, FVM. Okay, finite difference method, finite element method, finite volume method. So previously we have seen the stochastic method and deterministic methods. So the broad classification, under this there are so many methods, but in general in CFD we come across with these methods. These are the prime methods that are being used worldwide. Now we'll see in detail what are these methods are about. The first one is finite difference method. So the finite difference method, it is the oldest method actually. Of the three, it is the oldest method. It was being used almost from 18th century onwards. It is easiest method for simple geometries. Say suppose the geometry is like this, a rectangle. Okay, and it is having some parts. So this kind of simple geometries, it is very easy to use this method, and it can be applied to any grade, but for the structured grids or regular uniform grids like this, it is very easy. For if I say suppose if I use a triangular mesh, then it is going to be little difficult. So by in principle we can use for any grid this kind of FDM, but in application, if you see, in general this FDM is used only for structured grids. Okay, if I am going to use for any other grids, unstructured grids, then I have to do some strenuous process and then I will get the result. It doesn't mean that I will not get result. For structural grids, it gives the results very easily. Okay, that is why it is said very simple and effective. See here, higher order schemes on regular grids. Okay, say suppose I have first order, second order, third order, fourth order, fifth order, sixth order, any order. Okay, the order means x power 4, x power 5, like that. If the function is having the power of 5 or 6 or 7, any higher order schemes, it is very easy for the regular grids. Regular grids in the sense structured grids. Now the in FDM functions are represented by their values at certain grid points and derivatives are approximated through differences in these values. So what is the meaning of that? You can see here. So this is an example here. Here these are the node points. If I say this function is represented in the form of differences here. Okay, f2 minus f1 by delta x. So the function, the partial differentiation is replaced by, so the difference. So this is the way you use the FDM. So what do we do first? First we divide the grid into equal pieces. Okay, equal points, and it is called the grid points. So equally distributed grids means, as I have already discussed, this is equally distributed grids. The grid points represent the discrete positions in space at which the solution values are obtained. So what are these grid points are about? These grid points are representing the space. Okay, some x and y values. Each grid point will have some x and y values, and these grid points are representing some discrete points. This is representing a particular point, this is representing a particular point, like that. There are all these different grid points are representing different positions in the space. Okay, the continuous derivatives in the governing equations are replaced with finite difference approximations. That is what I have said. So here, say suppose we have dou u by dou x and dou rho by dou t, dou u by dou y, like that. All these terms are there in our governing equations. All these equations are replaced by the finite difference approximations. So for doing this approximation, for replacing this value, these functions or these partial differentiations with the finite difference approximation, this delta x must be very small. Okay, I cannot take 1 meter distance, I can substitute the differences. Okay, so the difference should be very small. Certain formulations of finite element methods define on regular grid are identical to finite difference method on the same grid. So if you see regular grids, if I see, and if I apply the FEM method, okay, finite element method and finite difference method, if the grid is uniform like this, I may get the similar, or the application of FEM and FEM are identical, okay, only for this kind of uniform structural grids. Now this what we do, we replace the partial differentiations with the finite difference approximations. Now how this partial difference finite difference approximations are obtained? By interpolating between the discrete values of the functions over a small neighborhood. So here, so if I want the, here at this point I need the finite difference approximation. So what I have to do, neighboring points I have to take, and using the neighboring points I can get the finite difference approximations. The derivative of the function at each grid point can then be computed using the derived polynomials. So the partial differentiations are replaced with these finite difference approximations, and finally you will get the polynomial functions. And the polynomials are solved at each grid point, okay. The the partial differentiations are approximated with finite difference approximations to the polynomials, and these polynomials are computed, okay, at each grid point. So the finite difference method is frequently used in acoustics and ultrasounds, where it is well suited to broadband and time domain problems, is relatively simple and formulate and implement, okay, where the application is very simple like this, the broadband and time domain problems. See, the sound and acoustics, they are dependent on time. Now in this time bound problems, since the acoustics are applied in the room, the space, so here I can easily uniformly discretize the domain. So in this kind of scenarios where the domain can be easily discretized into a uniform structure grids, in such kind of situations we can easily apply this FDM. So that is what is said here. And the FDM is having some advantages and disadvantages. We'll see here. Higher order accuracy, okay. If I increase the element order, say suppose if I say this element, the grid points are like this. Say suppose if I reduce the grid point distance between these 2 points, I will get higher accuracy. So easily I can get a higher accuracy. Then rectangular grids. This FEM, if we will see further, the FEM involves in multiplying with weight residuals and manipulations and all those things. So this FEM, it is simple finite difference approximations. So for regular structured grids, FVM is very easy than FEM. Okay, sorry, FDM is very easy than FEM and FVM. FVM is finite volume method and FEM is finite element method. So our FDM is easier to apply than these two in rectangular grids or regular grids scenario. Okay, but here I have some difficulty. So these are the advantages. We have to see disadvantages also. Say suppose I have a curve like this, okay, or we will make it little complicated. Say suppose the boundary is like this. So if I want to divide this domain into rectangles, it is little difficult. Or we will see a realistic scenario. See here, a aerofoil is there, and here one sharp corner is there, here this is there. So if I want to divide this into uniform rectangular grid kind of structure, it will be very difficult. Okay, it will take lot of time, and because if I want to make it uniform, I will get millions of elements for this small one, because I have corners here and have complex shapes here. Okay, now in this kind of scenario, the FDM application is having some difficulty, because we have to use we cannot discretize this into uniform rectangular grid. Say suppose here in this kind of scenario, if I want to use local refinement, say suppose here I want a small grid, and here in this region I want a coarser grid, and this is a fine grid and a coarser grid. What do you mean by fine grid? The elements are very small like this, and here the coarser grid means like this. So here I want finer grid and here I want coarser grid. In this kind of local grid refinement or adaptive mesh refinement is required, then in such kind of situations FDM is having lot of difficulty. So these are the advantages and disadvantages of FDM. Now we will move on to FEM. Now FEM, this is the grid for FDM and this is the grid for FEM. Okay, so FEM is similar to FEM in many ways. Okay, so how it is similar? Here also we are dividing and here also we are dividing. So that is the only way it is similar. Here we are dividing the domain into finer parts called grid, and here also we are dividing the grid into small parts. This is also a grid. Now in contrast to finite difference method, the grid is usually unstructured. Okay, both are having grids, that is a similarity, but here we use the structured uniform grid and here we use unstructured grids. In case of 2D cases, we will see triangles or quadrilaterals. Okay, in 3D scenario we will see tetrahedrals and hexahedral elements. So what is a tetrahedral means? We will have 4 triangles. So 4 triangles if I combine, I will get a tetrahedral. And hexahedral means I will get if I join 6 squares or 6 rectangles like that. So the hexahedral and tetrahedral elements are used for 3-dimensional, and triangles and quadrilaterals are used in 2-dimensional things, 2-dimensional problems. Now FEM is analogous. Say suppose a circle is there, okay, and I am dividing this circle into number of parts. If this distance is approximated as a straight line and I can add up the lengths of all those straight lines, I can find out the perimeter of the circle. Okay, so this is one analogy which is similar to this FEM, or the FEM is similar to this analogy. Now the FEM is used in finding approximate solutions. Okay, here we will get approximate solutions for differential equations. Okay, here we will get the approximate solutions, but here we have a chance of refining and getting the error to an appreciable value. We will get the error within some acceptable value. So the distinguished feature of FEM is that equations are multiplied with weight functions before they are used over the domain. So in FDM, directly we are taking the equations and we are applying the finite difference approximation. But in the case of the FEM, what we do, we will multiply with some weight residual functions. Okay, that we will see in detail in when we are discussing in detail about the FEM. Such functions can be constructed from its values at the corners of the elements. So these weight residuals, these functions, weight functions, will calculate the weight functions from the end values. Okay, we know these boundary conditions, and from these boundary conditions, we'll get the weight functions for the given structure, given grid, and we'll take these weight functions and multiply with the partial differential equations and then implement the finite element method. And these weight functions generally are usually of the same form. It can be of different form, but usually they will all for all the elements will have the same weight functions. In FEM, the region of interest is divided into grid points. So this point is common for FDM, FEM and FVM. So what we'll do, we'll divide the entire grid into number of parts. In FDM, we divided into structured uniform grid. In FEM, we can divide it anyway. We don't have to bother about which type of grid you are using in FEM. Okay. It uses variational methods to minimize the error function. So as I said earlier, I get an approximate solution if I use FEM. If I use the variational methods, then the error can be minimized. It cannot be made zero. It can be minimized to get a stable solution or acceptable solution. Before discretization, the governing equations are rewritten in integral form. In FDM, directly we have taken the partial differential equations and we have applied the finite difference approximations. But in case of FEM, what we are doing, we are converting them into integral form, and these are also called as weak forms, and then we are solving. Okay, so that is the difference between FEM and FDM. That is one more difference. The result is non-linear algebraic equations. So here we will not get a linear algebraic equations, we will get a non-linear algebraic equations. In FDM, we will get a linear algebraic equations. If we see history, FEM is applied to structural analysis only. Okay, the aircraft structures, they started applying this FEM for aircraft structures, and then it is extended to many areas. Now they started some softwares, some softwares which are designed for a particular case. They are not applicable for all the cases. Some codes which are generated for some particular application, there people are using this FEM. And what kind of people will use? Who are familiar with FEM applications with structural analysis. Okay, those people are doing structural analysis for a long time and they are familiar with FEM. So they are trying to implement this FEM to the CFD problems for a particular case. Okay. So nowadays they are using in, as I said, in multiphysics, CFD and electromagnetics. Now, what are the advantages and disadvantages of FEM? I cannot say FEM is not having any disadvantages. Okay, so it is having a lot of advantages and disadvantages also. So the main advantage is arbitrary geometries. So the geometry can be of any shape like this. Okay. Any shape geometry can be there, and it can be having a sharp edges also like this. Any shape, this FEM can be applied with little effort. But in case of FDM, we have to make a lot of effort if the shape is not an uniform one. Say suppose a rectangle, if I take, very easy. If I want to cut this aerofoil section inside that, then it will be very difficult in case of FDM and very little difficult in case of FEM. So the grids can easily be refined or subdivided. So suppose I want, as I said, I want a refinement. Okay. So the aerofoil, I am interested, the boundary layer, what happens inside the boundary layer, I want to study. So if I want to the entire grid, if I want to refine and make it small, it will be a laborious process. I mean, the calculations will be laborious. So what I can do, I can use a finer grid at this point, and I can use a coarser grid at this point, and use this finite element analysis very easily. Now, what is the disadvantage of FEM? The disadvantage of FEM is inefficient for solving many time-bound problems. So this is the advantages for finite difference problems. Finite difference method, you can easily apply it for the time domain problems. FEM is very difficult, or it will not, sometimes it will give wrong answers when I apply for time domain problems. It is easy to increase the order of elements so that the physics fields can be approximated very accurately. Okay, so the order of the elements, the size of the or the number of the elements can be increased so that I can get the physics very nearer to the idealistic solution. Okay, or nearer to the accurate solutions. So this is about the FEM. Now we will see about the FVM, finite volume method. So finite volume method is representing and evaluating partial differentiation equations in the form of algebraic equations. It is similar to FDM and FEM. Okay. It is similar to FDM and FEM, it is said. How it is similar in the sense, again the domain has to be divided. See, the domain has to be divided into smaller parts are called grid or mesh. Okay, so the meshing is the common feature for all the three things. Okay, so here we divide the domain into volumes, finite volumes. This itself is saying it is for three-dimensional problems. It is not for a two-dimensional problem. It is for a three-dimensional problem. Say suppose I want a two-dimensional problem. How to do that? What I have to do, say suppose this is I have a surface like this. I can extrude it little bit so that it will become a volume, and then I can discrete this into finite volumes, and then I can analyze. So finite volumes also are used for solving two-dimensional problems. What they do, they will extrude it little bit so that it will become a finite volume problem. Okay. So the finite volumes refer to small volumes surrounding each node point in the mesh. We'll see here. So this is the node point. Okay. So the node point, around the node point, I can consider the control volume, or the control volume can be in between these nodes. Okay, it can be surrounding the nodes, or it can be in between the nodes. And generally, these are the different shapes of finite volumes that we generally see. So this is a tetrahedron, this is a square pyramid, and this is a hexahedron, and this is a triangular prism. Now, the finite volume integrals in partial differential equation that contain a divergence term are converted to surface integral using divergence theorem. This we have already seen. When we are doing the derivations for physical meaning of divergence and other cases, when we come across with the surface integral, we converted that into volume integral. Okay, this conversion is based on the Gauss divergence theorem. Now here we are doing the same thing. So what we are doing, we are divergence term. We are having this divergence term in volumetric form. This divergence term is converted back to integral form surface integrals using this Gauss divergence theorem, and then the finite volume method is applied. The finite volume method's strength is that it only needs to do flux evaluation for cell boundaries. So we have seen in the case of control volume. So in control volume, what we are interested? We are interested only in the flux, the mass per unit area, mass flux, the momentum per unit area, momentum flux, the energy per unit area, energy flux. So what we are interested in FVM, because we are dealing with control volumes. So as we say the control volume, the interest is only the flux evaluation. Okay. Now the FVM is a natural choice for CFD problems. In CFD, generally we are interested in the flux, all the flux terms. So most of the commercial softwares are based on FVM. Almost all the commercial softwares like Fluent, CFD, all those things, sorry, CFX, Fluent, CFX, Star CCM, all the commercial softwares, they are using FVM technique for solving CFD problems. Okay. Another advantage of finite volume method is it easily formulated to allow unstructured meshes. Same thing. Similar to FEM, in FVM also we can use unstructured meshes. FDM, we have to use only structured uniform meshes. So the functions that approximate the solution when using FVM cannot be easily made of higher order equations. So here the difficulty with FEM is we cannot solve the higher order terms here. So we cannot solve up to second order. But if you see the governing equations, all the governing equations are having only second order. For the general computational fluid dynamic problems, all the governing equations are of second order only. So the finite volume method can be easily applied for CFD problems. Are there any other methods? We'll look into two special methods. Okay, one is mesh free method. What do you mean by mesh free method? Mesh free method in the sense we are not dividing, we are not having these elements like this, we are just having the nodes. We'll have some points randomly and will not connect these points. Will not connect these points. We'll just solve the equations at these random points. Okay. So this kind of techniques are special techniques called mesh free method. The other one is multi-grid method. So multi-grid method in the sense we'll have a finer grid and we have a coarser grid together. So it is not a special method, but generally it is it is categorized as a special method. Okay. So the multi-grid methods, they generally use in FVM also we can use, and FEM also you can use this multi-grid. So what is the main idea of multi-grid? It is to accelerate the convergence of a basic iterative method by global correction from time to time, accomplished by solving coarser problem. Okay. So here we will solve the coarser problem, and then here we will solve with the finer grid. So in this way we'll reduce the iteration time. Okay, solving time will reduce. If I have to divide the entire one into finer grid, it will take a lot of time. So in order to reduce the time, what we'll do, we'll divide this grid into different grids and then we'll solve. Thank you. Now we'll just have an overview what we have discussed in this class. First, the finite difference method. We have seen before finite difference method, we have seen the deterministic models and stochastic models. So that is just introduction for numerical methods. The main interest in terms of CFD is on FDM, FVM and FEM. So FVM, finite volume method, is easily applicable to the CFD problems. So all the softwares, the commercial softwares that are available in the market, they are based on finite volume method. So what is finite volume method? We are dividing the domain into finite volumes. So finite volume means it is a three-dimensional. So all the three-dimensional problems are flow problems. Now if I have a two-dimensional problem, what I will do? I will extrude it to some height and make it the two-dimensional problem into three-dimensional problem, and then I will solve using the finite volume method. So using this technique, all the commercial softwares are designed. Now can I apply FEM and FDM? Now people have started using FDM and FEM techniques. Those who are working a long time with FEM, okay, for structural analysis and all those things, now they started using this FEM technique for fluid flow problems and heat flow problems. And some researchers, what they are doing, they are writing their own code in FDM, finite difference method, for solving their particular problems. Okay, so this is about the numerical methods that are used for CFD. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.